Welcome everyone to our solar photovoltaics course 6th module. Today we are having the third lecture. We have already started with the perovskite solar cell. In the last two lectures we have discussed about the basic components of a perovskite solar cell. We discussed about what are the advantages of the perovskite solar cell, and we also discussed how to fabricate a perovskite solar cell, what are the different components of a perovskite solar cells. In today's lecture, we will discuss about the different kind of geometry or the orientation that is possible in a perovskite solar cell, and how this kind of geometry or the orientation can lead to the interesting photophysics in this perovskite solar cell. So, device fabrication continued. The direct bandgap lead halide perovskite can be used as absorbers in thin film solar cells due to their large absorption coefficient in the visible regions. The typical device structure of perovskite solar cells we have already discussed and also have been shown in the subsequent figures. In the mesoporous structure, the perovskite absorbable layer is deposited on a mesoporous electrical contact. How can you get a mesoporous electrical contact? So, what is the photoanode we have? We have ITO coated glass substrate or FTO coated glass substrate as the photoanode. Now, we mentioned that we can put a layer of titanium dioxide on top of that. Now, this TiO2 layer we can make it a mesoporous or a planar layer. So, if we make a mesoporous TiO2 structure by heating the titanium dioxide in pH3 acetic acid solution after making the film at 450 degrees Celsius, we can make a mesoporous TiO2 layer. And if we use this mesoporous TiO2 layer as a electrical contact, then the resultant device will be a mesoporous photovoltaic devices. Similarly, the planar structure is fabricated on a planar contact. So, if we do not want to make a corrugated porous structure, if we just have a planar TiO2 layer, then we will have a planar photovoltaic devices. Furthermore, the structures can be classified into regular and inverted, where the fabrication order of the charge transport layer is reversed. That is, the extraction directions of the electrons and holes with respect to the illumination direction are opposite. So, basically this thing we have already discussed. We call them as a NIP geometry and PIN geometry. Some people or in some textbook it is also called as regular and inverted structure. The solar cell structures are similar to that of dye sensitized solar cells and apparently differ from the PN junction used for silicon and gallium arsenide. This has its origin in the initial perovskite solar cell research, which was an extension of research on dye sensitized solar cells. Yeah. So, this is a very interesting story on that. So, when people were working on the dye sensitized solar cell, and it was very popular, we routinely get efficiency of 8 to 10%. Now, the first time the perovskite was used as a sensitizer molecule. When you say that a decent efficiency of 3.8%, that time perovskite material was used as a sensitizer molecule in a DSSC geometry. Later on it was found that not only as an absorber, but perovskite can also act like a hole transport material. Then people thought that okay, why do not we use the same material as a sensitizer and as well as a hole transport material. So, that gives rise to the efficiency enhancement in the perovskite solar cell, and then it was found that the efficiency is quite high even without doing any surface modification. With some surface modification we can get even a higher efficiency. So, that is why all the people who are working on the sensitizer based solar cell, they have also started working on perovskite solar cell. The high efficiency perovskite solar cell are based on the heterostructure, in which the light absorbing perovskite layer is sandwiched between p and n type semiconductor layers to selectively extract the electrons and holes. In every structure, the energy level of each layer is smoothly connected with that of the neighboring layer. So, whenever we build up the successive layers, we have to make sure about the energetics, or we have to make sure about the position of their HOMO energy level and LUMO energy level, so that a proper electron transfer can happen in them. The perovskite, the prerequisite for the perovskite solar cells with a high photovoltaic conversion efficiency is the fabrication of a high quality perovskite layer. This is somewhat similar to the organic solar cell. You remember when we discussed about the organic solar cell, we talked about the morphology, and we say that in an ideal organic solar cell we require a bicontinuous phase separated percolated network. Why bicontinuous phase separated? Because in organic solar cell we generate exciton, bound electron hole pair, and these excitons are generated in a donor material. we need to bring an acceptor material in the vicinity of the donor to separate the charge carriers to electrons and holes. So that electron goes in one way and hole goes in another way. Now, we have to have a lot of this optimized nano interface throughout the geometry in a bulk heterojunction solar cell, so that the charge carrier can hop from one side to the another side. Now, the physics of the perovskite solar cell is little bit, the photophysics of the perovskite solar cell is somewhat different from the organic solar cell. Unlike exciton's behavior, here you have a free charge carrier behavior. Here the electrons and holes are not tightly bound by the electrostatic force, they are free charge carriers. So, we do not need to bring another material to separate the charge carrier. But what is required? A very good quality, a large uniform, pinhole free or crack free continuous thin films of the perovskite. So, the phase separated bicontinuous percolated network in the organic solar cell is now replaced by a continuous uniform pinhole free large area perovskite films. If we have a continuous uniform and pinhole free perovskite layer, then the electrons and hole can easily percolate or transport using this layer. But very often it is difficult to obtain a uniform layer with a very high quality and pinhole free regions. So, that comes in the domain of the morphology optimization in the perovskite solar cell. Like before, we will see that this morphology optimization relates to the photophysics of the devices. As you can understood that if the morphology optimization is not good, if there are a lot of pinholes in the film, so these pinholes acts like a trap states. Now, there can be two different kind of trap states or defect states in the perovskite layer. Some of the trap states lies on top surface, they are called shallow trap states, and some of the trap states they are buried inside the bulk of the material, they are called deep trap states. Now, both this kind of trap states, while shallow trap or deep trap, they act as a source of charge carrier recombination, or they act like a place for charge carrier recombination. So, in an ideal device we should not have lot of traps in the device. So, we need to passivate those traps. There are ways to passivate these traps or neutralize these traps by putting different material layers on top of the perovskite material. And by doing time resolved spectroscopy like femtosecond time fluorescence decay experiment, we can find out by doing an intensity dependent study how many trap or defect states are there in the perovskite layer, where they are located, so that we can optimize those trap states to make a pinhole free films. So, as usual the morphology is always related to the photophysics of the device. So, let us take a look about the device fabrications. So, if you remember, we have talked about two different kind of geometry. One is the mesoporous structure, another was the planar structure, and we also talked about PIN or NIP geometry or regular or inverted geometry. Now, it is possible to have a mesoporous or inverted mesoporous or the planar structure in either regular or in inverted. So, based on that there are 4 different combinations of this perovskite solar cell is possible. So, for example, you look at this picture here, if we have a regular perovskite solar cell with a mesostructured orientations. So, I have a glass substrate, transparent electrode, ETL or electron transport layer, perovskite, hole transport layer and metal electrode. Whereas a plane structure things, the regular plane structure, glass substrate, transparent electrode, ETL, perovskite, HTL and metal electrode. So, in both of these case it is a regular structure. So, that is why I have the ETL electron transport layer with the ITO contact and hole transport layer at the metal contact. But in the first example this is mesoporous. So, the TiO2 layer is mesoporous, you can see from the figure we have drawn the circular things here, and here we did not draw any circular thing, this is a plane things. So, one of them is a mesoporous layer, another is a plane layer. On the other hand, you look at the inverted structure here, here it will be other way round, glass substrate, transparent electrode, hole transport layer and electron transport layer in between the perovskite. So, what is the difference from these two figures? Here the electron transport layer was near the ITO, but now hole transport layer is near the ITO. There the HTL was near the metal electrode, now the ETL is near the metal electrode. So, basically they have now inverted from the regular structure. Now, it can be also be mesoporous like this, or it can be plain like this. So, there are 4 different configuration is possible: regular mesostructured, regular planar structured, inverted mesostructured, or inverted planar structured. The heterojunction structure in the figure sandwich the MEPBI3 absorber layer with the charge transport layers, FTO, compact TiO2 which can be mesoporous TiO2, perovskite and spirometrid, and finally the gold, where FTO, fluorine doped tin oxide, is used as a transparent electrode, and TiO2 and spirometrid, they are typically as an electron and hole transport material. So, TiO2 is an electron transport material, and spirometrid, which has this big name inside this bracket, it is a small molecule, this is a hole transport materials. So, it can be either an electron transport material and we are using a hole transport material along with our perovskite layer. Their energy levels allow efficient spatial separation of the photo generated electrons holes from the perovskite layer and their selective transport to the electrical contacts. So, they not only help to separate the charge carriers, but they also help to selectively transport the charge carriers to the corresponding photo anodes or photocathodes or corresponding the photo electrodes. If you look the stacking of the devices, we can also draw in terms of the energy band diagram. For example, here you see that this is the FTO layer, then on top of that there is a TiO2 layer, then we have the perovskite layer MEPBI3, in top of that we have a spirometrid layer, and finally the gold layer. Now, when the light absorbs in the active layer, so both electrons and holes are created. Electron is injected to the TiO2 because its conduction band is lower than the LUMO energy level of the perovskite layer, and from there electron is injected to the FTO and finally it goes to the outside circuit, whereas the hole which lives here, that goes to the spirometrid, from there it goes to the metal electrode. So, this way the circuit completes. Fabrication of perovskite solar cell we already discussed, but what is most interesting thing is here when we discussed about the different orientation and the morphology is the photophysics of the perovskite solar cell. Later on we will see that there are a lot of engineering aspect to optimize the morphology of the perovskite solar cell, and each of them will lead to an interesting photophysics. So, what we mean by the photophysics of a perovskite solar cell? Here a generalized scheme of the dynamic interplay of the various photophysical process and relaxation mechanisms in bare CH3NH3 lead iodide or CH3NH3 lead iodide X chlorine X perovskite thin film is shown in the figure. Following photo excitation at low light intensity, electron hole pairs generated. So, basically we generate electron hole pairs following photo excitation at low light intensity. These generated electron hole pairs will rapidly form highly delocalized 1-year excitons with their binding energies comparable to the room temperature thermal energies. As a result, spontaneous dissociation of the excitons would occur, leading to a coexistence of excitons and free carrier populations in the bare films. So, the first process in any solar cell is the exciton generation or charge carrier generation. So, similarly, when light falls on the perovskite material, electron hole pairs are generated. The first stage is fulfilled. Then whatever the electron hole pair is generated, they are now delocalized, and this kind of delocalized excitons are called 1-year excitons. If the excitons are very strongly bound and not delocalized, they are called Frenkel excitons. And this 1-year excitons, their binding energy is comparable to the room temperature thermal energies. So, if their binding energy is comparable to the room temperature thermal energy, what will happen? So, thermal energy is enough energetic to break this binding energy of the excitons. So, it will spontaneously dissociate the excitons into the free charge carrier, or the bound electron hole pair will now dissociate to a free charge carrier. So, in addition to the bound excitons, we have now free carrier population in our perovskite film. Monomolecular or first order recombination process such as bound electron hole pair or geminate recombination and trap assisted recombination are found to be insignificant. At stronger light intensity, bimolecular or second order recombination process like the recombination between a free electron and a free hole or non-geminate recombination is also extremely low, with at least 2 to 4 orders lower compared to be calculated by Langevin recombination. So, there are various kind of recombinations. Recombination is the electron hole pair annihilation. Now, there can be various process of recombination happens. The recombination can be bound electron hole pair, this is called the geminate recombination or the monomolecular recombination or the first order recombination. Now, in perovskite this geminate recombination probability is also low. There can be trap assisted recombinations. So, there are the existence of this geminate recombination and the trap assisted recombination, but if you have a very uniform continuous film or a very uniform continuous pinhole free film, then you do not have a lot of trap assisted recombination. So, that is why both the band to band recombination or the geminate recombination as well as trap assisted recombination is insignificant for this perovskite material. Now, when we increase the intensity of the light, if you increase the intensity of the light, then the second order recombination that becomes very dominant. Second order recombination is a free electron hole recombination or non-geminate recombinations. Now, the probability of non-geminate recombination is also low, at least 2 to 4 order lower compared to the calculated Langevin recombination model in the perovskite material. Now, because of this low recombination, we will have an excellent charge carrier transport to the electrodes, and that leads to the high short circuit current in this kind of device. Now, what left is the multi-particle third order Auger recombination process. So, the multi-particle recombination is now dominant, but eventually losses out to amplified stimulated emission or ASE or lasing at even higher pump fluence with optical gain possibly from the electron hole plasma formation. So, there are 3 different kind of recombination can happen in any optoelectronics devices. Okay. So, the first is the first order recombination, sometimes called the geminate recombination. This is due to the band to band recombination or bound electron hole pair recombination. There can be trap assisted recombination. If you go to the high intensity of the light, then the second order recombination becomes dominant. Second order recombination is the free electron hole recombination. This is also called a non-geminate recombination, and there are third order recombination or multi-particle Auger recombination. Now, in the case of the perovskite, both the first order and second order recombination is insignificant, but due to the presence of the exciton and the free charge carrier simultaneously, the multi-particle Auger recombinations become prevalent in this kind of system. But finally, what happens, this multi-particle recombinations they lead to the ASE or lasing phenomena at high pump fluence intensity. In bare perovskite films and without charge extraction, the photoexcited species excitons and free carriers undergo radiative, luminescence or non-radiative process within the perovskite. Typically, under solar light intensities at low intensity exciton, Auger recombination or ASE would be strongly suppressed. So, if I use the low intensity excitation, then the Auger recombination is not very strong effect, but if I use the high intensity radiation, then the Auger recombination become dominant. Experimentally, by doing a femtosecond time resolved spectroscopy, one can find out the different components of these recombinations. From the decay dynamics of the excited charge carriers, one can find out whether it is a first order recombination, second order recombination or an Auger recombination. With the non-radiative pathways, geminate recombination, trap assisted recombination and Auger recombination, weak or inactive under solar light intensities, it is therefore understandable that these perovskites make excellent photovoltaic and light emitting materials. Now, what are the source of the non-radiating pathways? First of all, the geminate recombination or first order band to band recombination. It can be trap assisted recombination and it can be Auger recombination or multi-particle recombination. Both this geminate recombination or trap assisted recombination or Auger recombination, they are all non-radiative pathways. So, that means they do not emit the light. So, that is why they are weak or inactive under solar light intensities, and therefore, if the non-radiative emissions is there or if the non-radiative pathways are weak, so then the radiative pathways has to be very strong. That is why this kind of direct bandgap materials are also suitable for fabrications not only for photovoltaic devices but also for the light emitting diodes. Let us take a look of this band diagram or a schematic figure of the whole photophysics of a perovskite solar cell. So, what happens when light absorbs, we create an electron hole pair. Now, this bound electron hole pair we call it as an exciton. Now, if the exciton they are weakly bound, if this is a 1 year excitons, this is a weakly bound, then we see a geminate recombination. So, the electron can go and couple with the hole, it is a monomolecular recombination. Similarly, these excitons, this probability is very weak. This exciton can disintegrate to the free charge carrier. So, electron and holes is now free and they can wander around using this active material geometry. Now, two cases can be possible between this free electron hole pair. If there is a weak intensity of the light, then there will be a non-geminate recombination or second order recombination, free charge carrier, free electron hole recombination, or there can be trap assisted recombination. These electrons and hole when they travel along the films, if there are defect states or trap states is there like shallow trap states or deep trap states, then electrons and hole can fall upon on those trap states and these trap states are a potential energy minima. So, they can get recombined there. So, the free charge carriers can undergo two different kinds of recombination, non-geminate recombination which happens under the weak intensity of the light, or it can be trap assisted recombination. Now, if the morphology of the film is very good, then we can discard this trap assisted recombination. Exciton under the weak intensity they go the geminate recombination, that means band to band recombination. Now, if you have a strong intensity of the light, then what will happen, an amplified spontaneous emission or multiparticle Auger recombination. In a multiparticle Auger recombination, it is a trimolecular recombination. So, the electron hole can combine with another electron, or here there can be further amplified emissions is here. So, to summarize this whole process once again, adjacents of the light they generate a bound electron hole pair, but these electrons and hole pairs are now bound loosely. So, there are two things can happen, either this bound electron hole pair can disintegrate to a free charge carrier, free electrons hole, or they can undergo under the weak intensity of the light band to band geminate recombinations, and this is a monomolecular recombinations. Now, when you have a free charge carrier decay, then the free charge carrier they can undergo two different kinds of recombination. Under the weak intensity of the light they can be a non-geminate recombination which is the free electron hole recombination, it is a second order recombination, or there can be trap assisted recombination. If there are a lot of trap states or a lot of defect states in the material, then that can be trap assisted recombination. If the morphology of the perovskite film is very good, then we can suppress this route of the recombination. Now, the third possibility is that if the light intensity is very strong, then there can be spontaneous amplified emission or can be Auger recombination or multiparticle recombinations. Now, all these three different mechanisms can happen from the perovskite material. Now, depending upon the morphology, we can suppress one of this route. Now, if their electron hole pair is recombined, then what will happen? If the electron hole pair is recombined radiatively, then we will get the light. If it is recombined non-radiatively, then we will get the heat. So, all the source of non-radiative pathways, as we discussed in the last slide, if you go back to the last slide, all the source of the non-radiative pathways like geminate recombination, like first order recombination, trap assisted recombination, free charge carrier recombinations, and the Auger recombination, the third order recombination under the strong intensity of the light. These are all non-radiative pathways. First order geminate recombination, trap assisted recombination, and Auger recombinations. These are all non-radiative source of the light. That means this kind of recombination does not give the light, they are weak. So, which is strong is the bimolecular recombination or non-geminate recombination in the perovskite. And if there is a bimolecular or non-geminate recombination is there, then we will get a radiation of the light out of this circuit. So, that is why the photophysics tells us like this materials is good for fabricating light emitting diodes also. Except the fact although what we learned that this photophysics is excellent in the perovskite material, but there are some problems also with the perovskite materials. For example, some of the challenge of the perovskite solar cells are improving efficiency to exceed thin film cadmium telluride solar cell. Now, thin film cadmium telluride solar cell has already achieved like 16 to 18% or even 20% efficiency in an ideal condition, and which are very stable. But perovskite solar cell although has reached that number, but the stability is very poor. So, by understanding their material properties and the optimal cell designs, one can improve the efficiency. But the most important challenge is the increasing air and temperature stability. We will discuss in details later on about this air and temperature stability and how we can prevent this instability, because there are a lot of research interests now ongoing on to make a stable air processable ambient condition stable perovskite solar cell. Replacing the toxic lead with a greener element. Now, we said that when you have this perovskite material CH3, NH3, lead iodide, we have lead in this material, but lead is toxic. Although we use lead in the battery, but still there is a possibility of the environmental leaching. So, we do not want lead to have in the systems. So, that is why a lot of research interest is ongoing to replace the lead with non-lead material, for example, bismuth or silicon. So, these are called lead free perovskite. One of the problem with the lead free perovskite is their efficiency is not very high, although their stability is very high in comparison to the lead based device. So, the current challenge is to improve the lead free perovskite solar cells efficiency. Finally, is the AMX3 perovskite structure the best stoichiometry? Have we tried other structures? There are a lot of interest is now going, instead of the single perovskite structure, to make a double perovskite structure or a layered perovskite structure, which is called the quasi perovskite, 3D 2D perovskite structure or a 2D perovskite structure, or like try a completely different kind of stoichiometry or the geometry in the perovskite structure and see whether that is also good enough for the charge carrier transport. So, these are all challenges in the fields which needs to be optimized for a better understanding of the photophysics of the device. And as we have seen that in many cases the morphology and photophysics, they are correlated. If we have a very good morphology, then we have a control over our photophysical properties, even if we have a good materials. And some of the current challenge like stability and the toxicity of the lead is addressed by developing the methods to counteract the photo instability, thermal instability as well as the moisture instability. In our next lecture, we will discuss about the stability issue of the perovskite solar cell, which is one of the major issue which prevents the commercialization of these devices. And then we will see that once we address the photo instability issue, then we can also address the thermal instability and moisture instability, and it is possible to make a air processable completely stable perovskite solar cell with a decent 8 to 10% efficiency, even higher than that. So, the possibility of making roll to roll perovskite solar module is not very far away, and if it is possible, then the dream of making the solar cells at a extremely low cost in a roll to roll flexible substrate can be achieved. Now, whatever we have discussed today regarding the photophysics of the perovskite, as I said that lot of research papers and review papers, excellent research papers and review papers, if you search online you will get it. For example, you can also read this photophysics of metal halide perovskites from materials to devices by Yosoki, Kanemitsu and Takio Handa. This is a very good reference to look into and understand the basic concept of the photophysics of the perovskite. But there are a lot of these very excellent review papers on the photophysics of the perovskite materials, which one can also look for better understanding. Thank you for your attention.